In this lecture, I will discuss the important concept of permutations and combinations. Both permutations and combinations fall in the area of combinatorics, which is an area of mathematics primarily concerned with counting, both as a means as well as an end in obtaining results. So when we count number of combinations we can have, we are basically practicing combinatorics. First of all, let's discuss permutations. Permutations are an arrangement of objects in which their order or sequence is important. For example, each arrangement of the numbers 4, 6, 7 and 9 can give rise to different numbers. For example, 4679, 6749, 7946, etc. Here the order is important. Although they are the same 4 digits, but still they make up 3 different numbers in these 3 different combinations. Also, here you can see another example of permutations where we have 3 balls, red, blue and green, and these are the different permutations possible for these 3 balls. So how to calculate permutations? There are a couple of methods. We have the fundamental counting principle. This is the most elementary method of calculating permutations. It is also known as FCP. And another one is by using factorials. And finally, we have the formula for calculating permutations. Let's discuss fundamental counting principle FCP first. Fundamental counting principle basically states that if an event can be chosen in A different ways and another independent event can be chosen in B different ways, the number of different arrangements or permutations of these events is A multiplied by B. So consider a choice A with 4 options and a choice B with 5 different options. If you had to choose an option from A and then another option from B, the overall total number of options would be 4 multiplied by 5 or 20. Here is an example of fundamental counting principle. You have 4 t-shirts and 2 jeans. The total number of ways in which you can decide what to wear is 4 multiplied by 2, that would be 8. We can use fundamental counting principle by counting the number of slots and then counting the number of permutations. For example, so we can identify first the number of slots available for a particular thing and then identify the number of options for every slot. Finally, we multiply the two numbers to get the number of combinations. As an example, you have 50 students in a class and you have to select 3 out of those for the posts of president, vice president and general secretary. In how many ways can you do that? Oops, I missed an off here. Okay. So in how many ways can you do that? So let's see, we have 3 slots, one for president, one for vice president and one for general secretary. And we have 50 students. For the first slot, we can have any of the 50 students. For the second slot of vice president, because one student is picked, so now we are left with only 49 students. And finally, because 2 of the students have been picked for the vice president and president slots, now there are only left 48 students to choose from. So the number of combinations would be 50 multiplied by 49 multiplied by 48, whatever be the answer. So this will be the number of permutations for how many ways we can choose a president, a vice president and a general secretary from a class of 50 students. The next method for calculating permutations is by using factorials. Factorials are useful to count the possible arrangements of a set of distinct objects. For example, 3 children sit down in 3 fixed chairs lined up in a row. How many different seating arrangements are possible? So here, factorials can be used. So the number of ways of putting n distinct objects in order, if there are no restrictions whatsoever, is n factorial. And factorials are denoted by this exclamation sign. And these are calculated as n factorial would mean n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, all the way to 1. For example, if we want to calculate 7 factorial, we will have to use 7 multiplied by n minus 1 or 7 minus 1 or 6 and so on 5, 4, 3, 2 and 1. So 7 factorial would be 5040. This is how we calculate factorials. Okay, let's see another example of factorials. So how many ways can 10 cars park side by side in a parking lot? The answer is 10 factorial. So that would be 10 multiplied by 9 multiplied by 8 multiplied by 7 all the way to 1. Sometimes we see problems on the GRE for factorials when all items are not distinct. In that case, the number of mutually distinguishable permutations of n things taken all at a time, of which p are of one kind and q are of another, such that p plus q in total make up n, is given by n factorial divided by p factorial and q factorial. For example, we have 5 red, 4 white and 3 blue marbles in a bag. They are drawn one by one and arranged in a row. Assuming that all the 12 marbles are drawn, determine the number of different arrangements. Now here all the items are not distinct. There are a few red marbles, a few white marbles and blue marbles. So the number of possible arrangements can be calculated using this formula as 12 factorial divided by 5 factorial for 5 red marbles, 4 factorial for 4 white marbles and 3 factorial for 3 blue marbles, giving us the number of 27,720 instead of just 12 factorial. The third way by which we can calculate permutations is by using a permutations formula. In this case, the generalized formula of n different things taken r things at a time is given by permutations of n objects with r objects taken at a time, or npr, or p n comma r equals n factorial divided by n minus r factorial. This is the formula for calculating permutations. Let's see how we can apply it. How many different ways can the gold, silver and bronze medals be awarded in an Olympics event with 12 athletes competing? Now here we have 3 medals, gold, silver and bronze, and we have 12 athletes. Now how many different ways can they be awarded? So we have 12 athletes and we have to award 3 of the athletes. So we calculate the permutations accordingly. 12 factorial divided by 9 factorial. The answer is 1320. Okay, moving on to the next topic. After looking at permutations, now let's look at combinations. So here is an example of combinations. You have to choose 3 friends out of 10 to go with you on a hiking trip. Now clearly the order of friends or items does not matter. No matter if you choose friend number 1, 2 or 3, and no matter in which order you choose them, 2, 1 and 3 or 3, 1 and 2, they are basically the same set of 3 friends. So in combinations, the order does not matter, whereas in permutations, the order matters. And here is the formula for calculating combinations. We use n choose r or NCR, capital C letter here denotes combinations, and we use the formula of n factorial divided by r factorial multiplied by n minus r factorial. In how many ways can 5 sportsmen be selected from a group of 10? We use the formula 10 factorial divided by 5 factorial and then 10 minus 5 factorial or 5 factorial. The answer is 252. So how to know when you want to use permutations and when you want to use combinations? So in permutations, order matters. They are always more in number than combinations. But in combinations, order does not matter. And here are the 2 formulas side by side. Here is the formula for permutations, n factorial divided by n minus r factorial, and here is the formula for combinations, n factorial upon r factorial multiplied by n minus r factorial. See, this term in the denominator reduces the number of combinations. Alright, so how to distinguish permutations and combinations? For example, let's look at this problem. You have to select 3 people from faculty of a college to serve as president, vice president and secretary. This is a permutation problem because order matters here. One who is a president cannot be a vice president and cannot be a secretary either. In this problem, where you have to select 3 people from faculty of a college to be on a committee, this is a combination problem because the 3 people will be on a committee. The order does not matter. Okay, let's look at a problem. For the special at a restaurant, you can choose 3 different items from the 10 item menu. How many different types of meals could you get? So we have clearly a combination problem because order does not matter. You can choose any 3 different items. So it is 10 choose 3. So we can use the formula for combinations as 10 factorial divided by 3 factorial multiplied by 10 minus 3 factorial, or 10 factorial divided by 3 factorial multiplied by 7 factorial. Now we can expand 10 factorial as 10, 9, 8 and multiplied by 7 factorial divided by 3 factorial multiplied by 7 factorial. Now we can cancel 7 factorials and we are left with, let me write it here, 10 multiplied by 9 multiplied by 8 divided by 3 factorial, which is 3 multiplied by 2 multiplied by 1. Now we can solve it as 720 divided by 6 or 120. So 120 different types of meals we can get, so that's our right answer. Okay, let's look at another problem. In how many ways can the letters of the word merciful be rearranged such that the vowels always appear together? Here are our familiar set of 5 options, but let's solve it. Now here we have a condition that vowels should always appear together. E, I and U, these are the 3 vowels present in this word merciful. All the words are distinct. So we can consider the 3 vowels as one set, E, I and U, and the rest of the words M, R, C, F and L, these as separate words. Now how many different combinations can these vowels have? If we rearrange them, these will be 3 factorial or 6. And also, how many different combinations can be possible for this set of 5 different alphabets? M, R, C, F and L. These can be 5 factorial. So in total, they will be 5 factorial multiplied by 3 factorial. 3 factorial we have already calculated as 6 multiplied by 5 factorial, or 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, or 120. So the total number of combinations here will be 720. So C is our right answer. Okay, in this short lecture we looked at permutations and combinations, and we looked at distinguishing situations where order does or does not matter. Order matters in case of permutations, but in case of combinations, order does not matter.